Okay, Assalamualaikum and good afternoon. All right, so today is supposed to be my talk, for which I prepared not many slides. I think it's not quite sure how many, just a few slides, I think. So let me just this. So you can see this. So I decided to look into no. This is actually prompted by Hazaze's work, okay, in some sense, because I was looking to how spaces, subspaces of, say, CP1, sort of, you get this orthogonality relationship on it. So in a way, it's supposed to be, moving towards that. So, but I have not come to the point where I have completed reading all the details of uh, the papers by Bertram. It's Wolfgang Bertram. So, but interesting idea, which has been there for some time, and then probably what Bertram did is to sort of geometrize all these so-called algebras that was lying there. So let me go next. Just first thing, just preliminaries, and then I'll look at Bertram's geometric completion. The sectioning is not so quite correct, but never mind. So let's go back to the roots. So if you remember, quantum theory is essentially the construction is rather ad hoc, okay, coming from a set of mathematical rules rather than physical principles. So one could perhaps look at relativity, for example, which is based on the idea of, say, initial observers and things like that, which led to a very simple set of physical ideas regarding inertial frames and so on and so forth. In the quantum theory setting, there is no such principle, and we are given this set of mathematical rules that we need to obey to construct the framework for quantum theory. So most of you have already gone through quantum mechanics, and you know that the most basic way to describe quantum theory is through Hilbert spaces, and this is again, why do you need these Hilbert spaces? No one really knows. Okay, but this is essentially largely the formalism that people follow, at least even when one goes to a kind of generalization, it still goes back to Hilbert space description to make comparisons whether they are on the right track or not. Okay, so how do you get these Hilbert spaces? Are usually from quantizing physical systems. Normally you think of a system of a particle, or you can have even multiple particles. And how do you do the quantization? Essentially, there are many different programs, and they do not necessarily give you equivalent results. Okay, there are quantization programs that do not lead to Hilbert spaces, at least directly. One could construct Hilbert spaces with additional steps. For example, path integrals and so-called deformation quantization, which are really quantization on the phase space itself. Okay, so it's not right. It's not quite the Hilbert space. But now with new developments of quantum information science. For example, there are attempts to reconstruct quantum theory from a set of physical principles, normally in terms of measurements and what can be done with the physical systems. So these are attempts to reconstruct, and Bob Cooker's work is again an example of how you can actually reconstruct quantum theory using category theory. Okay, but usually what happens, even in the case of those who are constructing quantum theory from information theory point of view, one read Christopher Fuchs, is it? He's Christopher Fuchs, one of the physicists who believe in the informational what you call aspects of quantum theory, based on Bayesian statistics. Okay, but again, information is again about what? Okay, so there must be some underlying physical system, and then what can you actually say about the physical system itself, which leads to that particular information. So this is perhaps if you look at some of the Christopher Fuchs paper, it tries to address this, but again, no, there is that particular question in mind. So what else I want to say about this slide? Right, okay. Okay, then let me go on to the next slide, just in case I remember some of the things I want to say. Okay, as I said, there are quantum theory is built on mathematical tools, okay, or techniques, and one of the problems that if you want to reconstruct quantum theory is that there are many facets of quantum theory that you need to take care of. It's not just a single thing. It's not just about doing Hilbert spaces and that's it. Okay, so there are many other things that needs to be you need to be concerned about. Okay, one of the things, perhaps the best review that I can actually see is this review. Can you see the cursor, by the way? Anyone? Yes. So one of the best, one of the almost what you call comprehensive review of mathematical concepts and in quantum theory is done by Hishamuddin and Zainuddin. I think Hishamuddin, I'm not sure how to pronounce this, is a colleague of Tariq Ali. Okay, I think they know each other. So so he has this thick, more than I think nearly 200 pages, I think, of this review about mathematical concepts in quantum theory. So what are the things that one needs to be concerned about when you construct quantum theory? First is there is this idea of state observable duality. Now, how can one think of this? Is probably the best thing is to go back to the roots again, like before. You have different formalisms of quantum mechanics. You have Schrodinger wave mechanics, you have Heisenberg matrix mechanics. Now, what's the difference between the two is the fact that Schrodinger wave mechanics are based on states to be your primary object, okay? And Heisenberg matrix mechanics are based on observables, okay? So the observables become the primary objects of the quantum theory itself. So now we know that there are, apart from some technical details, we know that this Schrodinger wave mechanics and Heisenberg matrix mechanics are essentially equivalent formalisms of quantum mechanics. Okay, so so there is this duality between the two in some sense, and this duality also crops up in quantum information science. I think in the context of quantum channels and things like that. Okay, so I'm not prepared to say anything more than that, but you have that duality in mind. Now, this duality is you have to be careful. There is another duality that's involved, which is the idea of duality from coming from the inner products. Okay, so you have this idea of vectors in Hilbert space, and then you have so-called co-vectors. Okay, so this is needed essentially because you have the idea of your Hilbert spaces are essentially complex vector spaces. And for complex vector spaces, you have this internal operation. It's called involution, or no, in ordinary language, it's just complex conjugation. Okay, so that becomes an internal sort of symmetry, if you want. Okay, so this needs to be taken care of. Okay, the other one is the idea of convexity, so that one is able to handle mixed states. Okay, one of the early papers of quantum formalism was done by Bogdan Milnik. Okay, geometry quantum states. The recent review is in 2012 here about convex geometry. So he proposed that one should take into account convexity as a main ingredient inside your quantum theory. Now, for those who are working in quantization aspects, there is another concern about what you can actually do in quantum theory is really coming from the symmetries of the physical systems. Okay, so you need to be able to have certain symmetries in order for you to get information out. Okay, so the symmetries in some sense dictate the types of states and the types of observables. Now, the last thing is the one that seems to be, at least what I wanted to do is something along this line, is to look at the geometry of this. And geometry, what does it do? Okay, if we think in terms of, say, relativity, you have this so-called inertial frames, for example, with local coordinates. But in the end, those local coordinates doesn't really play what they call. I mean, it's just an artificial thing that one constructs for a particular inertial frame. Okay, so the real relativism, in some sense, is to be able to move from one inertial frame to another inertial frame. So the coordinates, in some sense, do not matter. For one to do calculations, of course, one uses the coordinates. Now, in quantum theory, you don't really have that. That's why to do quantum theory in a geometric sense seems to be a bit more difficult than it is supposed to be. Okay? Partly because historical reasons as well. Okay, so this is going to be short. Right. So what are the things that's but Wolfgang Bertram tries to do? Well, as I said, the conventional quantum theory begins with the Hilbert spaces, and Hilbert spaces are just vector spaces, of course, with other properties like norms. Okay, and this vector spaces has this distinguished point, the zero, okay, the null vector. And if you really think about it, it doesn't play any role as a physical state. So why do you have that distinguished point? Okay, in a way, you need that thing if you want to have the idea of, say, the abelian group acting on the vector space, then you probably need to have that. And then of course, yes, you have this idea of superposition principle, that you might want to also consider the null vector, so to speak. Okay, so you have this distinguished point that's there in the Hilbert space, but it doesn't really play a physical role. So what Bertram tries to do in sort of the maxim of Wolfgang Bertram is to say that all points should be created equal. Okay, so in other words, if there's no need for a distinguished point, you get rid of it. Of course, one already know that when you go from vector space with a distinguished point with the zero vector, okay, one can always go to the affine space. So more or less the affine space sort of mods out the translational symmetries, okay. So there one could actually really do that, okay, in the context of replacing the Hilbert space, so to speak. But one has to be careful of two things. One, first is you have that duality between states and observables. So if you remove this special point from the states, then one should also remove it from the observables. And the other one is, of course, the dual space. Okay, so this will be also place some kind of rule. So just to give an example, you have this space, the ordinary linear space that you often use in quantum mechanics is just the real line, for example. Of course, in Hilbert space, you replace this by some vector space or Euclidean space, okay, which you can sort of liken it to be your real line. So for simplicity, we just stick to the real line to start, and then this needs to be replaced by the affine equivalent for the real line. So in other words, there will be no distinguished points on the real line. Okay, one can look up some literature on that, and one looks at what we call the affine geometry. So the problem with this, when you don't have distinguished points like the zero thing, okay, how can you actually coordinatize space? Well, in that case, you need, instead of having points, you need some relations between points. So here one could actually use a triplet of points, A, B, C. Now, points can be there in the space, okay? The only thing that one get rid is this, what I call this distinguished notion of a zero, okay? So you can have points. So a zero can be a point in that space if you want, okay? But the idea is to not make any emphasis on that zero. So how can you actually do this? Is you use this idea of a triplet of points, and then you look for an invariant in that particular space, and that invariant is given by this ratio. Okay? This ratio R, which can be obtained from the difference between, the relative difference between 2 points. Okay, the ratio then. So one can do that. So in other words, once you have done this, you have to keep in mind the relationship with that invariant, and then one could simply if you plug in any translation, then you find that your invariant R doesn't change. So there's no problem with that. But for the case of the observables, remember observables classically is what? It's just a function from a particular space. M, for example, goes to the real line. So in this particular case, now one needs to replace this with the functions of M goes to the affine space. Okay, and there will be some similar invariants that you can build on this particular function space. Right. Now, the duality, once you do this sort of separately, for one for the real line or the vector space for that matter, and then do another one for the function space. Okay, then what is lost is the duality between the two, because you have different invariants. Okay, so one of the things is the idea of a affine space can be also altered in some sense to a different space called the projective geometry. Now, what's the difference between the two? The idea is, now, if we think about geometry as just simply the set of geometric objects, okay, so you have points, you have lines, and then so on and so forth. Okay, there is a distinguished set of lines in the vector space. The vectors which are parallel, they do not intersect. Okay, but other vectors which are not parallel, they do intersect. So we have this distinguished set of vectors, sort of making causing problems to this maxim of all points are created equal. Okay, so one wants to get rid of that distinguished set of parallel lines. Okay, and one does that by adding infinity into the picture. So parallel lines, while it doesn't intersect in the normal space or in the vector space or affine space, but you can make them intersect at infinity. And if you allow infinity to be added into the space as an extra point, then you get what we call the projective space. Okay, for example, RP1 will be essentially the real line with the infinity added onto it. Okay, so again, now comes back to the point of how do you coordinatize this. And again, in order to do that, we need some kind of invariant. Okay, so the invariant in this particular case is the cross ratio. Okay, so it's the ratio of the ratio that we had earlier on. Okay, so and this will be an invariant under the projective space. So again, from the previous experience with the affine space, one also need to do this for the case of the observables. So instead of functions going from M to R, you need to have functions from M to RP1. So Bertram actually coined this term called obstate, which is not a usual term that people use, but the idea is this is a combination of observable and state. Okay, so obstate, in a sense that one could flip-flop between the two in some sense. Okay. What else? Okay, the other thing that one also need is, just like when you have points in say vector spaces, you are able to form orderings that one can actually do with you need some kind of topology also there. But in this particular projective space, we have also ordering by looking at a triplet. Remember, the projective space, you need 4 points to define the cross ratio. Okay, the cross ratio here, but one will be if you want to think in terms of a relationship, one of them will be some reference point, okay, and then the other three will be the independent ones. So in other words, the ordering will be depend on on a triplet rather than a quadruplet, and this ordering is actually important for building logics. Okay. Okay. Now, we want to go over to quantum theory, and we know that quantum theory doesn't use real vector spaces, but they use complex vector spaces. So one of the things that one needs is to replace these real functions with complex functions rather than no, m goes to r. Okay. So here you have m goes to c, and c is a perfectly okay vector spaces. Okay, but again, there's a distinguished point in that particular vector space, so you need to go to the affine space, and of course, affine space. Then you have your vectors which are parallel to be distinguished. Then you go to the projective space. Okay, so the projective space in this particular case is the complex projective line. Now, this has the topology of the Riemann sphere, so I think most of you already know this. So so these are the set of lines that can be topologized as a sphere. Now you might think this is a bit odd because here is you consider as a line which is one dimensional, but it's a one complex dimensional line. So it's actually two real dimensions there. So and that two real dimensions form a sphere. Just like before, the up states or the observables and equivalent to the states will be a quadruple of CP1 functions rather than just a single function, because over there you can have four different values lying on the generalized corresponding to a particular what do you call, how should I say it? This relates with the idea when again when it goes to the point of doing the inner products. Okay, so there is that so you have some symmetries which are discrete corresponding to these four different values. Okay, so as I said, the inner product in the case of the complex case is a bit different from the real vector spaces. So you have this complex conjugation sort of playing a role there. So this complex conjugation in some sense will introduce the idea of a antipode map. Okay, so the map is given by that, and this antipode map actually gives rise to it's actually an anti-holomorphic map. Okay, so this anti-holomorphic map, if you compose together with your okay, I'm jumping ahead. If you compose your anti-holomorphic map alpha, which is the antipode map, with the complex conjugate map, which is not the anti-holomorphic map, then you can actually form a holomorphic map of order 2. And this different mappings, it sort of gives you some kind of automorphisms of no observables on CP1. Okay, so you get this idea of a Klein 4 group acting on CP1. So again, these symmetries do not really appear usually in the context of the normal quantization. I should mention that what we have discussed now is really only the classical case. We have not quantized anything yet. Okay, we are just looking at from the point of view what's available at the classical viewpoint. Now, it's a bit different when you compare this with the picture when you get from, say, quantization. You get the idea of CP1 after quantizing. Okay. Here, one get rid of this special points, special vectors, and then you get the CP1 as a classical thing. So this, in some way, is sort of corroborates the idea. I think if Omar is there, the idea of the complex projective space being classical. Okay. What makes quantum later on will be the following: is the idea of polarization. Okay, so in other words, you cut half of the degrees of freedom. So that I have not, because I have not completed the reading on Bertram's papers. I'm not sure how Bertram actually handles that. Okay. But let's move on. Okay. The last ingredient which I was hoping that I can read a little bit more and prepare a little bit more, is to include the idea of a Jordan product. Now, if any of you still remember, not sure how many of you are there, in the advanced mathematical physics class, introduced the idea of associative algebra. And what, so in other words, you can have products of elements of the algebra, sort of, to many orders if you want. But what happens is that you can actually get identities by modding out certain relations. For example, the commutator, you mod out by saying that, okay, how was it? I think this was the sort of skew symmetric, what you call, relation. So it was, you mod out that particular relation, then you get essentially the idea of a Lie algebra. Okay, and there is another one which is actually discussed by Jordan himself, together with the other two giants of quantum theory, was Neumann and Wigner. So they had a paper out, which is written down here, okay, which is in 1934. Remember, von Neumann wrote his book, complete his book in 1932. So this is after that book. And I'm not sure the letter he wrote to, what's the name of the guy? Where he said that he doesn't believe in Hilbert spaces. I'm not quite sure whether this is before or after. Okay, so, but in other words, this is a later development that, no, the idea is to consider this idea of Jordan product. Okay, maybe I should mention here that here is the generalized case where I have a fixed U inside as an element of the algebra, but in order for you to get back to the ordinary, say, Lie algebra, for example, you take U equals 1. Okay, and this one will be just like your symmetric ordering for your operators, for example. Okay, so what Bertram did here is where I could not finish the slides in some sense. What Bertram did is to consider these algebras and then the spaces that goes along with it. Okay, and then he has this set of spaces to consider instead of just a single space. Okay, so, and the idea then later on is to consider symmetric transformations within these spaces. Let me just how to go out of this full screen, escape. Anyone knows? Yeah, okay. Let me go to Bertram's paper. This is the picture of the four antipodal pairs where you get this Klein 4 group. Okay. Let me go down a little bit. Can you see the paper, by the way? I'm not sure. Let me just make this bigger a little bit. So see this is the set of spaces that one needs to consider. And what's involved there is already the idea of orthogonality, which is the thing that I hope to understand much better here, so that one could understand, perhaps construct what Ahmad has actually done in the symplectic blow up thing, so that you get something similar. Okay, so the idea you have to have all the spaces built into a single picture. Okay, so and work from Bertram is actually employing those kind of things. Okay, and of course there are other ingredients towards it, which is I already mentioned earlier, which is the symmetries. Okay, so the symmetries plays an important role because that actually tells you, what is possible to to go from one set of, say, like inertial frame to another set of inertial frame. Okay, so I think that's probably all that I can say for today because I have not finished. There is another second part of this essay which talks about the evolution of spaces. Okay, so that I have not gone through too much. So I think I will stop there. So let me get back to you. So that's it. So I welcome any questions at this point. No questions. So I understood everything. No, he goes direct into the projective space. And then with this inner product thing, there's this idea of a Hermitian space. And people has actually considered those as well. I think by Cirelli, I think the Italian paper. So why do we want to go into this thing is because you have this geometric sense to start with, and then with the geometric sense you talk about mappings and if you want to make connections with category theory, it's already no, because to me, okay, category theory is essentially just like how should I say? I don't want to offend any category theories, but the way I look at it is this: it's just what you can do with maps. Okay? So uh, the maps has to obey certain rules. Okay, so that essentially the way I see things at the moment. Okay, what? Well, if you remember, no, okay. If you remember, your blow up essentially is taking the distinguished point, and the distinguished point sort of goes back to CP1. Now, if you remember what I said earlier, the idea of why is this origin gives you this blowing up to the CP1 is because your origin, or in this case the zero vector, is orthogonal to all vectors. So you get back your CP1. So there, if you look back just now, remember that idea of orthogonality, the transversal, transversal, okay, or spaces comes in. But how it actually, no, the relation with the blow up, no, I mean, we still have to figure out what to do. Okay, that's the main thing. Any other questions or observation or gossips? It would be just like vectors, okay, but vectors without the origin. Yeah, that means you sort of you mod up your translations. Uh, what do you mean by complete in that sense? Um, it becomes more effective to describe the space without this so-called uh, extraneous points, okay, or distinguished points. Uh, the only thing is people rarely work with affine spaces because it's harder to describe coordinates. Uh, if, 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 if it's on the line, then it's unique. Now, if we talk of a different line, then it gives you another invariant. But in this case, you're talking about one-dimensional line, right? So there's only one. I'm done if everyone's done. So sorry I didn't get to complete what I wanted to say. Never mind. Maybe next time. So okay, I should end the recording now, I suppose.